Okay, well, we've been talking about using the tables. Uh, so recently, we've been talking about using property tables um, to find, let's say, I mean, it doesn't list every property, obviously, but uh, the idea of simple compressible substances is if you choose two properties, that's enough to define the state. So let's say talking about using property tables to find all properties uh, based on one or two chosen properties. Um, and it's been two properties if we're talking about liquid or vapor, and one property if we're talking about a saturated state. Uh, so now we're going to talk about some other ways of doing the same thing, some ways of calculating properties in terms of temperature or pressure, one or two other properties. So we'll learn a few ways to calculate uh, properties in terms of others, or properties as functions of other properties. Um, using simplified material models. Um, and so, for example, the ideal gas law is going to be one of these. We're simplifying a complex behavior of a gas to say that it behaves as an ideal gas, and in a lot of cases, you get really accurate results that way. That's the kind of simplification that we're going to talk about. So the first question is, um, why? Why not just use the tables if they do the same thing? You know what I mean? Uh, in both cases, what we're doing is figuring out a bunch of properties based on two given properties. Why not just keep using the tables? Um, the answer is that often you're trying to use a mixture of materials that you don't have a table for, or a single material that you don't have a table for. Um, so you don't always have access to tables for the material or the mixture of materials of interest. And also, so that's one reason that you would want to use these simplified models. Uh, Also, sometimes the tables don't go into the range that you want to deal with. Um, you might want properties beyond the ranges given in the tables. Um, Later on, like toward the very end of the class, we're going to talk about more complicated relationships, and we'll actually talk about the relationships that people use to construct those tables. Um, when they construct the tables, there's no way to really take um, take a measurement of like internal energy or internal entropy. Um, and so these things are calculated, but they're calculated with more complete, more complicated uh, models of the material. Right now, we're going to talk about simpler ones that work very well in some cases, but these are useful more in kind of like back of the envelope type calculations, getting sort of ballpark figures for these things. This isn't what you're using if you really need high accuracy. Okay. We're just going to go through these different models kind of one by one. And first, we're going to talk about liquids and solids. Um, and we're going to break this up into two different, uh, two models. The first one is where the specific volume is treated as a function of temperature. And the second one is treating it as incompressible, where the specific volume is treated as a constant. Um, so far, like if you dealt with any kind of thermodynamic stuff in your physics class, you most likely treated liquids as incompressible. If you've um, if you've ever, excuse me, um, so if you've ever like if you know remember talking about the density of water, for example, water has a density of 1,000 kilograms per cubic meter, if or 1 gram per cubic centimeter. If if that relationship sounds familiar to you, then what you're doing there is assuming that density is constant. And since density and specific volume are just reciprocals of each other, that means that you're assuming that the specific volume is constant. Okay. But as the temperature changes, specific volume changes too. We, I know I've talked in office hours with a couple people about this. When we did, there were a couple of problems where you did two variable interpolation of the specific volume of a liquid. You interpolated over pressure and temperature. And I don't know if you noticed, but you can go back and look at this. Um, when you look at when you do your interpolation over the temperature, you get a pretty big range in specific volume. And this is true of internal energy too. Um, but when you do your interpolation over the pressure variable, the the specific volume and the internal energy change very little compared to the temperature. And so that's what the idea here for part A here, and a lot of the ideas we're going to have is that these things change a lot with temperature. Uh, they don't change much with pressure, and we're going to keep seeing that theme. So the first one, so we're going to assume that volume changes with temperature. We're also going to assume that specific internal energy changes. So I'm going to list this again and just put them all in a list where, so specific volume is a function of temperature. Specific internal energy is a function of temperature. And specific enthalpy, we're going to assume is a function of temperature. And because these don't vary with pressure, we're going to assume that we can get accurate values for these directly from the saturation tables. Yeah, so let me finish this. So anyone remember what the definition of enthalpy was? Yeah, that's right. That's sort of the meaning is, but the mathematical definition, I mean, is it's the specific internal energy plus the pressure times the specific volume. Okay, that's the mathematical definition. And since we're assuming that these are only functions of temperature, we're going to assume that these values are accurate no matter what pressure you use. Okay, and if it can be at any pressure, then you might as well choose it at the pressure where your temperature is the saturation temperature. You know what I mean? Because that's easier to find stuff. So if you assume this model, then you can look all these up. In saturation tables as saturated liquids. Okay, so in other words, we're going to assume that this specific volume is the liquid. I'm going to put these sub F's in here because when you're looking at things in the saturation table, you have to choose whether you're looking at the saturated liquids or volumes. And we're going to assume that we can get accurate values from the saturated liquids for all these. Any questions about that? Okay, so in one of the ways that we can approximate liquids and solids, you can just look up all these values in the saturation table, even though it's a liquid. Okay, but if it's a gas, can you do this? No, because this is an approximation for liquids and solids only. Okay, well, we're not using solids. I guess you'd have to. We don't have tables for the saturation point, like the freezing melting point. There are tables like that, and you would use those if you're approximating solids. But for us, I mean, we're mostly focusing on liquids. Why are we mostly focusing on liquids instead of solids? That's just a practical decision, and it's because the kind of things that we're getting ready to understand, heat engines, refrigeration systems, stuff like that, they use the saturation point between liquids and gases. They don't use the saturation point between liquids and solids. So the second simplification is treating liquids and solids as incompressible. And that's when we're just going to assume that the specific volume is a constant. In other words, the density is a constant. For this model, we're going to assume, okay, so specific volume is a constant. We're going to assume that specific internal energy is a function of temperature only. Um, so these are our two assumptions. And we're going to get some things out of this. The first one is, let's think about those specific heat. Okay, so think about specific heat. We defined those last class. Remember that C sub V is defined as, anyone remember this? Partial of something with respect to temperature? U, yep. And we're doing this with the volume fixed or constant. And Cp is the partial of what with respect to temperature? Enthalpy. And with what fixed? Yeah, the thing I just wrote as I was waiting. Okay, so the subscripts are the variable that's fixed. And now let's think about what this incompressible assumption means for these. So with this incompressible assumption, CV is equal to the partial of U with respect to T with the volume constant. But we're assuming that that specific internal energy is just a function of temperature. So this is just equal to the total derivative of U with respect to temperature, and you don't have to worry about holding anything constant because that specific internal energy isn't a function of specific volume. And now let's think about Cp. That's equal to the partial of the enthalpy with respect to temperature, holding pressure constant. Enthalpy is U plus PV, but P is constant. So let's say, okay, so this is the partial with respect to temperature of U plus PV with P constant. But U is only a function of temperature. We're holding P constant, and we're assuming that V is constant. So this also gives you du d temperature. Okay, so these two things are equal. And so we're just going to call them both C. So CV is equal to Cp is equal to just C. There's no distinction between those if you're treating a material as incompressible. And you can look this up in a table. As a function of temperature. So what's the point of this? So this relationship, C is equal to the total derivative of U with respect to temperature lets us calculate the change in specific internal energy as a function of temperature given just value for the specific heat. Okay, this is for an incompressible treatment of a liquid or a solid. Let me show how this works. So let's say that we want to calculate the change in total internal energy and the change in total enthalpy. So these aren't specific, these are the extrinsic properties for 2 kilograms of liquid water. Going from a temperature of 320 Kelvin to 324 Kelvin. As pressure goes from, let's say, atmospheric pressure, so 101 times 10 to the third pascals to 140 times 10 to the third pascals. And we're going to assume a specific heat of, let's say, 4.18 kilojoules per kilogram times Kelvin. Well, first to calculate so our approach is going to be to calculate the change in specific internal energy using the specific heat, and then just multiply by the mass to get the total internal energy. So C is equal to du dt. And we can use separation of variables to write this as du is equal to C d temperature. And then we can integrate. So this one is from the start point to the end point. This one is from 320 Kelvin to 324 Kelvin. And so delta specific internal energy is equal to, if you integrate this, C temperature evaluated from 320 to 324. And so the change in internal energy is equal to 4.18 times 324 minus 320. And that's equal to about 16.7. 16.72 kilojoules per kilogram. And so then the change in extrinsic internal energy is 2 kilograms. That's what I said, right? 2 kilograms of water. So 2 kilograms times 16.72, and that's 33.44 kilojoules. For which one?
Right here. So why did you become changing?
Oh, yeah. Yeah. Well, when you integrate this, you're integrating from, you're integrating from the first state to the second state in both of these cases. You're integrating du from u at 320 degrees to u at 324. When you integrate, you get u evaluated from the start to the end, and that, another way of saying that is just the change in internal energy.
So could we have, going back, when we integrated energy, could we ever get a delta E rather than delta E?
When we integrated, yeah, so when we do those kind of problems, I'll write this up here and then I'll erase it after. But so we have dE dt is equal to Q dot minus W dot. And we come up with, dE dt is equal to some functions. And those were given as functions of time or as constants or whatever. So we get dE dt is equal to generally a function of time. And then we have dE is equal to f of t as a function of time, and then we integrate that. And yes, what we're always asked for in problems like that is the change in the energy or the change in the internal energy. So yeah, it's yeah. So what we're saying is, I guess the way I wrote it, it's sort of thinking about the same thing two different ways. The way I wrote it before, it sounds like, is I was imagining that our baseline for E is 0 at the first state, and then the change is just equal to E. It's kind of just removing the constant integration. Yes, it would probably be more careful to write it as a change. Yeah. Mm-hmm. Okay, so now we want to calculate the change in enthalpy. How are we going to do that? Well, specific enthalpy is defined as specific internal energy plus PV. And so for constant V, you can think of the change in enthalpy as being equal to the change in internal energy plus V dP. This is always true for the incompressible model. Always true for incompressible. Because we're treating that V as a constant. And so the change in specific enthalpy is equal to the change in internal specific energy. So that's 16.72 kilojoules per kilogram, plus the specific volume. So that's a constant. I'll deal with that in a second. Times the change in pressures. We're assuming that the pressure changes from 101 kilopascals to 140 kilopascals. So this is 140 times 10 to the third minus 101 times 10 to the third. And now we're going to assume that this, so remember, like when you did this kind of stuff in physics, the people who did it, you treated the density of water as a constant of 1,000 kilograms per cubic meter. So the reciprocal of that is the specific volume, and we're just going to treat that as 1 times 10 to the minus third. And so do that calculation, and you get that the specific enthalpy is equal to, I get 55.72 kilojoules per kilogram. And so the extrinsic enthalpy, capital H, is equal to 2 kilograms times 55.72. That's equal to 111.44 kilojoules. Any questions about that? Okay, so let me summarize this. What can we calculate? So notice for an incompressible material, first, if we're given the value of the specific heat, we can calculate. This isn't looking it isn't looking it up in a table. We can calculate the change in specific internal energy. And second, if we're given C and the specific volume, we can calculate change in specific enthalpy. No table needed. Yes. Between what? Oh, yeah. Yep.
But it seems that when you go back to the example, when you're calculating different changes of enthalpy and internal
hmm
energy, you have to look at them.
Why not just integrate dH dt? Is that? Yeah, that's not. So saying that, let's see. So what that says, du dt. Okay, so right, it's saying that, so it's saying that these two are equal to each other, but that's not saying that du. So du dt and dH dt, du dt and dH dt. Yeah, so that's where it comes from. So we're not assuming that enthalpy is a function of temperature. Okay, we're assuming that enthalpy. So we do assume that internal energy is a function of temperature alone, and yeah, and that's the only thing that we're assuming is just a function of temperature. This changes with temperature and pressure. So if you're holding pressure constant, okay, that's the key thing. If you hold the pressure constant here, then this partial derivative reduces to this. If you didn't hold the pressure constant, this could change and you'd get something different. And that's why otherwise, so right, we're not saying that dH dt is equal to du dt. This is the key thing that makes this equal to, this equal to this. Yeah, that's just, the only reason I did that was to show that we're not dealing with two different kinds of specific heats for incompressible materials. We're just dealing with a C. If you get that, you can calculate a bunch of stuff. So with vapors, we're not gonna be able to reduce it. We're gonna have those two separate specific heats, and we're gonna have to deal with them each independently. Any other questions? Okay, so this is useful, and if you so remember that if you don't have, this is the thing I want you to remember. This is quizzy. It's a very quizzy kind of statement. So remember that if you need to calculate the change in internal energy or the change in enthalpy for a liquid or a solid, usually a liquid, and you don't have a more precise way to do it, you can use this approximation to calculate it. Okay, if it's a liquid, you're losing a little bit of accuracy by assuming it's incompressible, but it's a lot better than nothing. Okay, now let's talk about one that is going to be useful all the time. So now we're talking about, let's see. Okay, so this is everything that we're talking about with liquids and solids. Now we're going to go to vapors. And with liquids, we had two different models. For vapors, there's only one, and that's the ideal gas model. By the way, vapors and gas, I sort of go back and forth between those, but there is a difference between those. It's kind of not a real technical difference, but people tend to refer to gases as things that at atmospheric conditions are gases. So like air is a gas, nitrogen is a gas, carbon dioxide is a gas, and the things that are liquids or solids at atmospheric pressure, when you turn those into, when you make those evaporate and they turn into a gas, those are what you call vapors. So for example, steam is a vapor because it isn't steam at standard atmospheric conditions, you know. Yeah, well, so yes, that is, so there is always some amount of evaporated water in the atmosphere. That has to do with the partial pressure. There's a very low partial pressure of water in the atmosphere, and so there's a little bit of evaporation, but yeah, I don't. But I guess yeah, I don't really have anything real clear to say about that. Okay, no problem. Um, all right, so ideal gas law. This is going to be super important. Um, so this fact is amazing. Um, for any gas, um, with a lowish, that's a technical term, and or a highish temperature, and we're talking about compared to the critical temperature and pressure. Um, the limit as the pressure goes to zero of P times the molar specific volume divided by the temperature is equal to the same value. It doesn't matter what gas that is. And that value is the universal gas constant. I think usually in the past you've called that capital R. We're going to call it R bar because it's a per mole calculation. And the value of that is 8.314 kilojoules per kilomole. Ooh, that sounds violent. Times Kelvin. Okay, that's amazing. And we're going to take full advantage of that. So how does this work? The idea is as the molecules spread out, and or move faster, molecular forces become insignificant compared to contact forces. Okay, that's what this is. That's what this phenomenon is based on. If the molecules are moving slowly, the temperature is low. Or if the molecules are really close together, then you start to pick up these molecular effects where when they get close to each other, they try to hang on to each other. When they get too close to each other, they try to repel each other. And those things, those forces become important. But if the pressure gets low and you let them spread out, or if you make sure that they're always moving really fast, this set of molecules that has attraction and repulsion with each other essentially just turns into a whole bunch of rubber balls. And all that happens that's significant is just these things bouncing off of each other and bouncing off the walls. Okay. And yes. Mm-hmm. The killas, yes, you can. I'm gonna. Yeah, that's equal to 8.314 in SI units. Yep. So if you reorder this, so this says it's a limit as pressure goes to zero. Well, we're only going to apply this relationship with low pressures. And so we're going to, since we have low pressures anyways, we're going to leave off the limit thing, and we come up with this ideal gas law. In a molar form that says P times the molar volume is equal to the universal gas constant times the temperature. I'm not going to put a box around this one because this isn't the one we're going to tend to use. The reason we're not going to tend to use it is because with tables and the calculations we do, it's always easier for us to calculate the specific volume per kilogram. And so we're going to define a new gas constant, R, that's equal to the universal gas constant divided by big M, where big M is mass of the gas per mole. Okay, so what I want you to notice here is this, R bar, the one we're not going to end up using, is universal. That's the incredible thing. The one we are going to use is specific to the gas that you're using. That's not universal. Okay, it's not universal because if you take a mole of carbon dioxide molecules and compare it to a mole of oxygen molecules, the M is different. And so that R is going to be different. But if you do this, you get the equations that we are going to use. The first one is that P, specific volume per mass, is equal to this RT. That's going to be the form that's useful to us. We're also going to use the fact that U, the specific internal energy, is a function of temperature alone. And H is equal to U, function of temperature alone, plus R times temperature. And those second two are, the second and third one, they're derivable from the first relation. We also have, so a couple of other relationships that, so these are kind of the things that define an ideal gas, but you can also simplify the calculations of the specific heats. CV and CP. CV is just du dt again. The reasoning is exactly the same as it was for an incompressible liquid. And CP is CV plus R. And again, these R's are not universal. You have to calculate that for each specific gas that you're dealing with. Any questions about that? The diatomic molecules. That's right. Oh yeah, it's molecule by molecule. Yeah. So you're treating one CO2 molecule as a rubber ball. Yep, exactly. Okay, let's do an example. So let's say that we have 0.5 kilograms of air in a fixed tank. And we add heat. So you add heat to this tank by putting the tank over a fire or whatever. Add heat. And the temperature goes from T1 of 20 degrees Celsius and pressure 1 of 101 times 10 to the third pascals to a pressure P2 of 202 times 10 to the third pascals, so 2 atmospheres. Assume that air has a mass of 29 kilograms per kilomole. And we want to calculate the temperature T2 at that higher pressure. Okay, well, we know that PV is equal to RT. We can calculate R. That's equal to 8.314. And that's in units of kilojoules. So I'm going to write it out as kilojoules over kilomole times Kelvin. And then that's divided by 29 kilograms, and we have kilomoles on top. We cancel these kilomoles, and you get that R in SI units is equal to 286.69. So the number you get is 0.2866, but that's in kilojoules. So if you're going to write it in joules, it's 286.69 joules per kilogram times Kelvin. We can't go, so we know that that temperature at state 2 is going to be PV over R, but we can't calculate that yet until we know what the specific volume is. So we can use that first state to calculate the specific volume. So at state 1, specific volume 1 is equal to 286.69 times the initial temperature. And in this equation, I didn't stress this when I gave this equation, but these temperatures have to be absolute temperatures. We're not talking about a difference in temperature, so this has to be in Kelvin or Rankine. So what's 20 degrees Celsius in Kelvin? 293, yep. Divided by the pressure, which at state 1 is 1.01 times 10 to the 5th. And we get a specific volume that's equal to 0.832 cubic meters per kilogram. Okay, what good does it do us to know the specific volume at state 1? We need the specific volume at state 2. It's the same for two reasons. The tank is fixed, so the volume isn't changing, and no material is going in or out. It's locked in there, so the mass stays the same, and so the specific volume has to stay the same. And so this is V1, and it's also equal to V2. tank with no material in or out. So now we can use at state 2, temperature 2 is equal to P2 V2 over R, and that's equal to 2.02 times 10 to the 5th times 0.832. And then R, I have everything now in SI units. And just like somebody foreshadowed here, so I gave this universal. Oh, well, we're not talking about that anyways. We already dealt with all that. So we're dividing by the specific R for air. So divided by 286.69. And you get a temperature T2 of 586.22 Kelvin. To Kelvin, that's all. Any questions about that? So I think most people in here have probably taken like a chemistry 1 where you use the ideal gas law for stuff. We're just going to use it in a different format. If you tried to use the form that you're more familiar with, eventually you just switch because it's more convenient to be doing it in terms of the specific variables that we're dealing with. Was there a question over here? Anyone? Okay. Okay, so what do we know about ideal gases? Oh, am I? Yeah. So just like we did with incompressible liquids, for ideal gases, what do we know? That's a great question. I will answer right now. Right now, when I finish this sentence. Period. That's from The Simpsons. That's a funny TV show. Okay, we know. No more stalling. Well, we know that first we can calculate any one of T specific volume or temperature given the other two. Okay, that's the key thing. We know we can use the ideal gas law. We also we know that we can calculate delta U, the specific internal energy, as CV delta T And third, we know that we can calculate CV or CP. Number two, remember that this CV, to use this formula, that CV can't change a lot. So this is for a CV that doesn't change much over the desired change in temperature. Okay, then the next thing we're going to talk about is polytropic processes. Let's do that next time. This is enough to do a couple of problems. Well, actually, no. Yeah, stop there. Okay, that's all. You don't have your notebooks. You're not going to have your notebooks.